Hello.
Am I audible now?
Yes, sir.
Okay. So let me. Hello. So good evening, everyone. So before starting, I want to collect some feedback about the exam in general. Not about MLT, just about MLT, how it was. It was easy, hard, moderate. Anyone who wants to give some suggestions about the exam?
So, like few questions, but like not related in the sense that the first question was not related to any linear regression or any model or anything. So we didn't know how to use those dot all or dot any function.
Which question you are talking about? That is symmetric or not?
Symmetric, yeah.
Yeah, so that was very pretty easy question, right? It's just about NumPy, or you can say it's from week 0, where you need to know the NumPy library.
It's actually a double for loop, nothing else.
Yeah, exactly. If you you just need to confirm whether X is equal to X transpose or not. That's it.
Yes, I did that, but it only passed 1 or 2 test cases. Like,
okay. I will check that. Obviously, your answers are with us, and we will check all the test cases. Not all the test cases, but for random, we will check. Okay, so we will try. If there is any issues with the portal or with the answer or concept, that we will surely take care of.
Yeah,
So
I
was
faced
there
it. Yeah, go ahead.
just to ask, like, was there any error in the perceptron question or
I think no. Which question, that accuracy part or that weight update part? Weight update. I think there's no issue, nothing wrong with the question.
Yeah, that was working.
Yeah.
I faced issue in the polynomial transform question.
Polynomial transformation was very easy. I think
No.
where you need to only write in the sequence. You have to write the powers of the features. If there are only 2 features, x1, x2, then you have the functions of return 1, x1, x2, x1 square, x2 square. If we have to return 3-degree polynomial, then x1 square, x1 cube, x2 cube. That's it, right? So even though you need not to you need not to write any other packages like iter tools or anything. You just can make use of NumPy and can return the powers of features. That's it.
Okay. I use the iter tools repeat without combination.
Yeah, that also you can use, but there was easy way to do that. If you go to the code that
My question is, Nitin, my question is, it did not like match the answers, means it was giving some error, technical error. I don't know whether it happened with others or not, but I was not able to, like, even though the code was correct, but the answer was not matching.
Okay, so here I think we are not discussing the solutions and actual answers. That we can discuss later. But I'm actually collecting the feedback in general about the exam. It was hard or easy, something like that. Not about the solutions of questions.
Yeah, the tricky part is when like sometimes we know the things, but it is hard to like remember everything. The editor part, where you don't get any help. So that is the part there where we struggle. At least I struggle.
Okay, but it is doable in 2 hours, right? 7 questions are enough in 2 hours. There are some easy questions, some tricky one you can say on few questions, but tricky. Where,
so if you remember the thing, then obviously 2 hours sufficient.
Yeah.
You have to remember.
so
I think 2 hours is sufficient. My experience is just that while debugging, if at all we end up, I mean, if you're completely clear about the code and just type it out like crazy, then you're okay.
Exactly.
But if you end up making even silly mistakes, the problem is we don't know in which line the error is.
Okay. So you want that portal should show what error your code is.
Correct. At least which line am I getting the error? So if I have more than
exactly.
5, 6
Yeah,
lines,
we got this feedback from other students as well. So we will try if we can do something about this problem. Rather than getting the actual output or your output or actual output, we can get the error what error you are getting. Right. So we'll see whether we can do this or not.
Yeah, and also, I mean, I think for many reasons you have also not allowed copy and paste of the same code on the same page. But I understand why you're doing it, but sometimes that is also difficult because if you want to try a portion of the code separately and run it separately, then we'll have to practically type out the whole thing or comment the whole thing. It gets a little difficult on the portal.
No, within the editor you can copy paste. There is a copy button.
Well, if I do Control C, Control V, it doesn't. Is
Yeah,
there a separate
Control C
mouse?
does not work, but there is a button at the top.
Okay. Maybe I didn't know that. Okay.
Yeah. So within the editor it allows, but from another.
But you are not allowed to use any other tab rather than portal, right? So where you will copy paste those?
No. See, I've written up a chunk of code, but I want to test a small portion of it. Then I'll have to comment out the whole thing, or I could just try an alternate method by just copying a portion of the code.
Yeah, got it.
So all that is not possible if you don't copy paste it. So. But that's okay. I mean, if there is a method, it's okay. I mean, I just thought Control C, Control V didn't work, so I thought there was no possibility.
Yeah. So other than errors, I think in case I want to debug the values of the variables, I have to print it, and if I submit it and then see the value in the output, it takes a lot of time. So that's
that we already see one thing. Okay. Kumar, you want to say something? You are not audible. Or you can write on the chat box because you are not audible at all.
Hello.
Yes. Yeah.
Oh, now I can. Oh, okay. Sorry. So there is a few things there. I want to point out in some need to develop in the portal. First thing, whenever we use the directory to get all the method, it's not showing in the portal. For example, sklearn, the sklearn dot data set is showing the working perfectly, but whenever I try to do that directory of sklearn dot data set, the directory is not coming in the portal. This is the first thing.
That portal has some all the packages are not installed in the portal. Only NumPy are allowed to use.
No, sir, sklearn is installed in portal. We can use.
But sir,
in the portal?
One second, sir. But one thing is there. We can use this particular function. We can use this particular model, but it's not showing in the directory. It is working. If I import, it is working, but it is not showing in the directory. That is the one thing. And second thing is, whenever suppose I do the directory and display, it's coming in the one line. And that line I want to copy to see that in the portal, because it's very hard to see all the method in the line, because you take the mouse there, it's hide that a scroll bar hiding everything. So it's hard to track that what's method, my method is wrong or right, sometimes spelling mistake. So that one thing is, and the copy paste is working in the portal itself, not working the outside of the portal. So what will happen if I want to take a copy of entire method and put in the portal and want to see that? So these two things is necessary.
Okay, we'll see that.
And one more thing about that polynomial transformation. I have regarding few questions here, sir. Since polynomial transformation came, whatever the theory we learn, the situation is completely changed in the exam.
Yeah, so we have given one example as well, right? One input output pair for that.
Yes. It's worked that all the cases passed, but the thing is that it consumes lots of time to rethink and redesign that entire algorithm from the beginning, because whatever the sir has did, it was the very straightforward, because they have taken the combination from the iter tools, and that all possibility was doing. After that, function tool was multiplying, so it was easy. Suddenly what happened, that they changed the combination, that the situation. So instead of polynomial transformation, all the possibility, instead of, it was asking only a square. Suppose it's the degree 2,
Yeah,
then
only the powers. Yeah.
square. So this algorithm completely changed, and it's took the lots of time, because
Yeah, so
we
you
need
can
to,
think this is a new question rather than we have made some changes in the question that we have in the on the assignments or on the lectures. We made some changes, little bit changes here and there. So this we cannot directly put the questions that we have in the assignments. We can have
I
one
got
or two or few questions, but not all the questions from directly from the assignments.
I
That's
think
why we are making some
here
changes
is,
in the actual questions.
yeah, point here is such questions take more time because
Yeah.
we have not seen that, we have to rethink. So time should be adjusted.
Yeah, so this is assessment, right? This is your assessment. How
Exactly.
to tackle with a new problem.
Yeah.
that
It's not just about the
Yeah,
problem
that
which
is
you have
fine. That
already
is
seen.
fine. Yeah, it's just a matter of time.
Yeah, the problem
That-
is with OPP is just that if you know everything, it takes 15-20 minutes to write all the 7 questions. If you get stuck, then 2 hours may be or may not be enough.
Right.
That's true with any OPP, I guess.
Exactly.
Yeah, obviously.
Right, the know everything means, I think it is important to know the method how we calculate, not a programming, because programming doesn't help so much. If we are clear the about that how method is moving, how the thing is working, we can do faster. So I realize one of the thing here, and one of the question top of that, once the sir you change that condition, then I have a question. Whatever the polynomial transformation we learn, is it necessary that this will be the fix in the real world, or in the real world also we need to, sometimes we need to create our polynomial transformation condition? Because
So it's a very subjective question. It depends upon the problem, right? It's not just in every cases you have to design polynomial transformation. So whenever we talk about polynomial transformation, it takes all such variables up to, let's say we are talking about degree 3, then powers of up to 3 and multiplication of different features as well. It includes everything. But in some of the cases, rare cases, you can find that only powers will work for you, right?
okay, so if it is the situation, then whenever, what about that situation,
Set
whenever
which is centered around circular data set which is centered around 0. There we need not to have the we only need to have only the powers term. That's it. That will work for us, right?
okay, so so now one more question on that. If it is the true, then whenever we use the sklearn dot, we take the polynomial transformation from the sklearn. So in that sklearn, everything is the fix, because the model is already the some algorithm is already predefined. So what happen if
Okay,
I
so
want
I
to?
think in sklearn library you have one parameter which you can set whether it takes the it takes the multiplication of features or not. I'm not correctly remember, but as
Interaction
far as
only.
I know, yeah, it has one parameter which you can set.
Set means that only the square term or the
Yeah,
something, or
yeah.
Yes.
To get only square terms or power terms, you can set one. I don't remember that exactly. Right.
okay, okay.
Okay, so should we start with week 9 now?
Mac has raised hand.
Okay, yeah. Yeah, Mehak, you want to say something?
Yes, sir. So for me, the problem wasn't the questions; it was the portal. I wrote code for every question. Like I knew how to solve all of them, but when there will be small mistake in syntax or anything, but I wouldn't know where is the mistake. So that's where I would struggle, and I would spend hours on that question when it doesn't require that much time. I was able to solve all the mock questions because I also use Collab to know where was the problem. But I cannot debug the code in the portal itself. So
Yeah, so the problem is if we get the error and what error you are getting, then it solves your problem.
yes,
Right?
sir. my marks won't be the reflection of my ability here this time.
Okay. Yeah, we'll definitely look into this, and we have already mentioned this to the team whether we can do this or not. So let's see whether it happens or not.
I think the best approach will be to use low use of collab.
Use of collab in MLT.
Yes.
No, I think this will not be possible.
Why? Means is there an issue?
How will you check the test cases?
Okay, but I'll put this point as well, but I don't see it gonna happen.
Okay.
Not- Okay, we are already 20 minutes late. We should start with week 9. So I guess nobody has started week 9 yet. You have already you have just finished your OPE yesterday. So how many of you have idea about the decision trees? So anyone who has studied the decision trees before?
Yes, sir. We use it in pretty much a lot of consulting work.
Where?
I work, so we use
Yeah,
it
okay.
for a lot of problem solving for our customers in financial services.
Okay. So how you will define a decision tree?
What do you mean by that? Let's clarify
so,
that.
So how you will explain? I mean, how you will say how the model looks like?
So it's one good thing is it's first of all it's graphical. Like you'll start on the top of the tree,
Okay.
and you'd use different features to split the data into what we call as rectangular shapes.
Rectangular spaces, yeah.
Right, and from an implementation standpoint, one beauty is any business user, particularly people without good understanding of math or stats, still they can understand it very well. So that's why it's very popular among business users.
Interpretability is a good one feature of decision trees, right?
Yeah, and implementation is very easy because it's a bunch of if then else conditions. So you can convert the tree into rule sets, and it can be implemented in any system using any language. So interpretability and usage is very good, and it has a lot of advantage over regression, because regression, you're fitting a linear model. Here you can, kind of essentially it's non-parametric.
Yeah, so yeah, this is one advantage for this decision tree as well. Yeah, correct, exactly correct. So let's try to understand what decision tree is. So is my screen visible? Whiteboard?
Yes.
Yes, sir.
Okay. So in the week 9 we are gonna cover decision trees. Okay, so before that we have seen different algorithm, and decision tree is completely different from all other things, and it's easy to understand and easy to interpret it as well. Okay, so first of all, decision tree is a non-parametric. So what I mean by non-parametric? What is non-parametric?
There are no hyperparameters.
You don't.
No.
You don't assume any.
Yeah. So
distribution of.
Yeah, so we don't make any assumption about the data sets, right? So we don't make any assumption about the distributions of data set. No assumptions about distribution of data set. So this is the one feature of decision tree, is a non-parametric. Second, it can be used for both classification and regression problems. Okay, so we will see how we can solve both classification and regression problem using decision tree. So let's first see what decision tree is. Okay, so I will explain using one easy example, very toy example, to understand what actually decision trees are. So let's assume we have a classification problem with two features, x1 and x2. Yeah. So let's say you have two features, x1 and x2, and we have a classification problem x, and your data set is somewhat distributed, something like that. It's not linearly separable, and you cannot find any that someone had mentioned that it's an advantage that if the data is not linearly separable or not distinct visible by some hyperplanes in the space, then we can use decision tree work well rather than the any other method, right? So let's say this thing. this is your data set. This is very toy data set, and assume your data set is something like that, distributed something like that. Okay. So these are two classes. Now I'm to learn a decision tree. For that, so what decision tree is, it takes the parameters and divides its input space into different spaces, different parts. So this is your two-dimensional input space. Taking one of these features, we divide our input space into different parts. Let's say I've chosen x1 features to divide my input space. Let's say how I will divide my input space by giving some threshold to this feature x1. I can say that whenever x1 is less than some value theta, let's say this value, let's say it is theta 1. So x1 is less than theta 1. My all the data set comes into this space. Let's say this is space A and this space B, and x1 is greater than theta. My space is the second space B space, and same way we can go. So this we can represent by the tree. Let's say this is your entire data set, which we call as the root node. Okay, so entire data set, which and we are dividing our data set into two parts. And using what we are using the we are making decision using the feature x1. So this is called a decision variable.
So I have
x1 is less than theta.
one doubt, sir. Sorry.
Yes.
Can we give a range of values in x, like x1 and x2, or is it has to be a single value?
No, mostly it's a binary tree. Binary tree means it splits its nodes into two parts.
Okay, right.
Okay, so we generally learn binary trees. Okay, so x1 is less than theta 1. We are learning. So here I am assuming that x1 and x2 are the continuous random variable, continuous features. Okay, we will see how to do split in case of the categorical variable as well. But here it's a classification problem with both the continuous features. Okay, now we have split our data set into two parts. Let's say this is A part and this is B part. So every points for which x1 is less than theta 1 goes to the space A, and or say region A, and all the data points for which the x1 is greater than theta is just a value. This is theta 1. If greater than theta 1, then that points belongs to B. So we have divided our input space into two parts, region A and region B. Now we can do similar kind of thing for A and B. So now A has this space. We can divide this space using, let's say I'm dividing this space using x2. Now I'm dividing using x2, and let's say I'm calling this theta 2, and I'm dividing in this way that if x2 is less than theta 2, then I'm dividing into this space. Let's say this space is C, and if x2 is greater than theta 2, then the space. So in this space, let's say it's space D. So I've divided again this space A into two parts using the decision variable x2, right? Feature x2. So in this way, we can generate our tree. So we can see here in the example. So can you see the screen?
We see the whiteboard.
Okay, only whiteboard. Okay, so if you see, let me see. Yeah, so let's say this is your data set. Okay, and you have two features x1 and x2, and now I'm dividing my input space into two parts using the variable x1. And how I'm dividing, if x1 is less than theta 1, I'm into region R1, and if it is x1 is greater than theta 1, I'm into the space R2. Now I've divided my data set into two parts, R1 and R2. I can make prediction in R1 and R2, but I can go further as well, right? Because if you see in the R1, the data set is distributed into, we cannot make accurate predictions because all the data set are equally distributed in region R1. So I will like to go further. I will like to divide further my region R1. So I'm dividing now region R1 by using the threshold theta 2 for the variable x2, right? Now, if I divide my region R1 into two parts using the variable x2, then if x2 is less than theta 2, I'm calling that part. So look at the region R3. So R3 is now my region, different region, and R4 is different region. If you see this regions R3, you can make prediction that if any points belongs to R3, I can predict it to be in the class blue. And if any points that belongs to region R4, I can predict it into the class red, right? Similarly, I can again divide the region R2 using some threshold for theta2. Using that decision variable as x2 and the threshold as theta3. So again, if I'm dividing this thing, and then again dividing the upper region as well using the decision variable x1, and in last I get this kind of decision tree. So it is easy to make predictions or easy to understand, right? So any new data set comes in, we will check from the starting. Let's say any new data set comes in, we will check whether x1 is less than theta1 or or greater than theta1. So if it is less than theta1, it goes left in the tree. Okay, so it means it is in the region R1. Now, if we will check if x2 is less than theta2 or greater than theta2. If it is less than theta3, theta2, then we call that point into the region R3. And how to make the prediction in R3? Because it's a classification problem. Here, we will the majority in that class wins. So if in R3, so here it is a pure node because all the data set belongs to class blue. So we will make prediction that if the points belongs to R3, that points it's predicted to be in the class blue. So for any new data set, if it belongs to R3, we will predict into the class 3. So that's how we will make prediction in the decision tree. So that's how a typical decision tree looks like. Okay.
What are these regions like? How do
Okay,
we?
so yeah, so how that is our next questions. How to find the optimal tree, right? How to design a tree. So we haven't talked about this. So I'm giving the general idea what is a decision tree. Okay. So any point up to here?
There were some misclassified points.
Yeah, there are some, right? We can again divide this region as well, and we can bound to stop there only. We can stop there as well. So that is manually set the threshold for the how large we want to grow our decision tree. Okay, so these are the points that we have to keep in mind and we need to answer. Okay, so how to define it? How to design a tree? So for designing a tree, now we need to answer few questions. Okay, give me 1 minute. Okay, so design a decision tree, we need to answer few questions like let's say we have features. So before that, let me explain what are the two different ways to design for different algorithm for a decision tree. We have in general in this course we have two algorithms. One is ID3 and second is CART. Okay, so actually these are the all those algorithms for decision trees are extended version of one another, or say improved version of one another. So first we will learn ID3 and then we'll improve this techniques to the CART. Okay, the same thing but we will improvise version of the ID3. Okay, so ID3 actually stands for iterative dichotomizers, and so this is actually means that how to divide your space iteratively. Okay, so and one more point that ID3 assumes that it takes only categorical variable. Okay, so this is one drawback of the ID3 algorithm. It takes only categorical features, and we will drop this assumptions in the CART algorithm. And in the CART algorithm, we can assume it can have both categorical and numerical features and mixture of both, right? So first we will learn about ID3 algorithm, then we will go to the CART algorithm. Okay, so our question was how to design a decision tree, right? for designing decision tree, we need to answer few questions like, let's say you have features x1, x2, x3, x4, and some variable by. So first I will talk about classification problem, then we will go to the regression problem. In this classification problem, y is my categories, right? Classes, different classes. So it is it's a categorical variable here, and all these variables I'm assuming to be for ID3 algorithm, I'm assuming all those features to be categorical. So all labels and category, all the features are categorical. Then how to decide how to design a decision tree? So for that, we need to answer few questions like which feature will be there at the root node. Okay, so few terminology that I want to explain. So the very first node or the entire data set is called root node. And the node in which we make prediction. Let's say your decision tree is looking like this, and we are splitting into this part. Again, we are splitting this region into this, and this region into this. So this is, let's assume this is a decision tree, and in this nodes we make predictions. Okay, so these are called leaves, and all other nodes are called branches. Okay, and for this node, this is the parent node of these nodes, and these are the child nodes of this parent node. Okay, so these are the child of this node, and or opposite, you can say this is the parent of these two nodes. Okay, so these are the childs of this node, and this is the parent of this node. So these are the terminology we generally use in the decision tree. So we need to answer which features to use at the root node, right?
So this branches is what? It's just two branches, left and right.
Yeah. So which nodes are used for making decisions? Okay, so here we are making these nodes we are using for making decision how to split our data set. These are called branches. Very first node is called root node, and the nodes in which we make the predictions. Here we make the predictions. So if the data set belongs to this node, we make predictions, right? So nodes which are used for predictions, those are called leaves.
So a leaf can also be a branch.
No, we only call them leaves, not branches.
Okay.
The leaves are the last ones, is it? And
last one. In the last one, we make the predictions.
The way we divide it is with the theta, right?
Yeah, the threshold. Okay, yeah. In case of categorical, in the case of so we decide the threshold in the case of numerical variable, numerical feature. But if it is categorical, let's say categorical is one feature x2. Okay, and it takes values 1, 2, and 3. So here we need not to decide the threshold how to split the according to x2. We just call them into three nodes. If it is x1, it's 1. If it is 2, if it is equal to 3. So here that's how we decide over the categorical features.
So in this right branch, what you've drawn, it's a branch. It starts with a branch, then it splits into two. Now the second one also you termed as branch.
This one,
the right one.
This one,
yeah.
This is a branch.
Now this is a branch. Then what is it split into? Two leaves or what?
So now we are splitting this, right?
So they are leaves.
So now if we are splitting, if we are using this to make prediction, if we are not further splitting this node, then we call it a leaf.
Okay. Okay, got it, sir. Thank you.
Okay. Okay. So for designing a tree, we need to answer which features to use at a root node. Right? So we have seen, let's say one example we have used in the lectures. So in this lecture, we have used this example. So in this example, we have 4 variables: outlook, temperature, humidity, wind, and all 4 features are categorical features, right? And the variable is no or yes. So we have binary classification problem here. So which variable you will choose for the root node? How you will decide that? So we need some kind of measure that will quantify which will give you the best split, right? So we need to define some measures for that. So for such findings as decision tree, we need to answer which attribute to choose for splitting. Attribute means feature, and what will be the splitting criteria. And so tree size we will talk about later. Okay, so these questions we need to answer. So data, you already know what data is. Model. So in the case of decision tree, trees itself are model. Okay, so if anyone asks you what is the model in a decision tree, tree itself is a model. So what is the procedure? We take the data set, we divide into two parts using some decision variable. What is decision variable? That we will come to later. And once we have split it into two nodes, again we take node and we'll split into the manner. So we will go top to down manner. And this algorithm is called Gini search. Why it is called Gini search? We will come to that as well once we see what happens there. Okay, so this data set we already talked about. Okay, so we were talking about how to measure that it is a good split or not. For that, we will define some measures. So these are called impurities measures. So first, defining impurity measures, we will let's talk about one notion here. Notion is probabilities. So if we are dividing PIK, I is the region, K is the number of classes. So PIK stands for the probability of the class K inside the region I. Okay, so it means how many data points belongs to region I upon total number of points, right? So here one is the indicator function. So it is one whenever by I equal to K. So it calculates the sum over such functions, calculates how many data points which are belongs to class K or belongs to region I, right? So this summation will calculate the number of data points which belongs to class K in region I and divided by total number of points in the region I. So this will give you the probability of the points which belongs to class K in the region I. Okay, so this is one notion. So one measure is misclassification error. So what it is just the number of data points which are misclassified. So how you make predictions? In the case of classification, we just take the majority class in that node and we will make the prediction according to that, right? So misclassification error will be what? Probability of points, or say proportion of the point which are misclassified. Okay, so it is generally Pi1 minus Piki, where Piki is the probability of the class Ki. Ki is what? Ki is the majority number of data points. It means it is the prediction. Ki is the prediction for that node I. And so what will be the proportion of classified example? 1 minus Pik, because Pik is the proportion of the classified example, correctly classified examples.
Sir, can you please explain this part with an example?
Okay, so let's say you have data point. Okay, so take a data point. Let's say two features x1, x2, and the label by. Okay, let's say data point 1, 2, 3, 4, 5, or something like 7, 8, 9. Just a random numbers I'm taking. And label here it is taking yes, no, yes, no. Okay, yes, no, yes, yes, no. Okay. Or we have taken more number of categories here. We can simply reduce into 1, 2, let's say 2, 2, 1, something 1, 2. Okay, and here we can take 0, 1, 0, 0, 1, something like that. So now you have two features and all x1 and x2 and the label by n1. Now let's say I'm dividing my space into two parts according to according to features x1. If x1 is 1, then all the data points goes to this node, left node, and if it is x1 is 2, all the data points goes to right node. Okay, so how many data points will be in the right node? Sorry, left node. So for which x1 is 1 goes to left node. So here x1 is 1, x1 is 1. So these 2 points goes to here. So here are 2 points. So one takes values yes and one takes value no. Okay, so if I'm to calculate the probability of yes in the node I, so that will be denoted by P. So let's call this node ith node, first node, and this is second node. Okay, so P1 of yes. So this probability will be what? So how many data points belongs to class yes? Only one data point belongs to class yes. And how many total data points are here in this node? 2 data points. So probability of points which are belongs to class yes in this node is 1/2. Similarly for this point. So what are the data points here? For all those data points for which x1 is 2. So these 3 data points belongs to this node, right? So in this we have 1 no and 2 yes, right? So if we calculate the probability of yes here, so what it will be? So 2 point belongs to class yes, and how many total points? 3. So this is the probability of class yes in this particular node. Or similarly, P1 will be what? P no will be what? 1/3. Okay, so if we make predictions, so here, if we make prediction here, we are not further splitting this. So what will be the prediction in this node? Because the majority is yes, right? So majority is yes, so we are making prediction yes here. So what will be the misclassification error for this particular node?
1/3.
1/3. The proportion of misclassified points. So how many are misclassified? Only one is misclassified. So this will be a misclassified point. So this is just for training error, but generally misclassification error is used for training data set, not for splitting. Okay, similarly here we have 1 yes, one no, so we are not making any decision here. We can further split into 2 parts, right? So if you see this data points here, it is 1 1, right? So these 2 data points belongs to here. And if you see the second variable here, x2 is 0 and 1. So we can divide this this node into 2 parts using the variable x2. So x2 is 0. X2 is 0, then we will we are into right node. And if x2 is 1, then we are in the right node. Okay. So what will be the data point here? So for which x2 is 1, right? So this data point will belongs to this node. So okay, so we will make prediction no, because only 1 point is here, and this point belongs to no. So we will make prediction in this node to be no, and in this node to be yes, because this data point belongs to this node and the label is yes. So we are making prediction yes, right? So these are called pure nodes. Pure nodes means what? If there is only one kind of data, one kind of data points there, I mean the data point which belongs to only one class. Let's say if we have 3 points here and all 3 belongs to class yes, then we will call this node to be pure node. Okay. And we need not to further split pure node because all the data set are of the same kind, same class. Got the point?
So sir, in the case of x1, we split it into 1 and 2. In that node 2, that has though we I mean came to the decision that this node will be a yes node, but it is not a pure node, no?
Yeah, it's not a pure node. If you want to split it, we can split it further.
Okay.
Okay.
So in this split, what you did, the pure node, so there's a 50-50% chance. So how will we decide?
Sorry, which node you are talking about? Node 1.
Yeah, node 1. In the pure node, there's a 50% chance of
no, in this node, all the data points belongs to class yes. Right?
Okay. Right, got it. Okay.
So prediction here will be class yes, and in this node prediction will be no, because all the data points belongs to class no.
Right, got it.
Sir, aren't we learning all the examples, which means we are going to overfit?
Yeah, exactly. So decision trees are tend to overfit. This is the very big problem with the decision tree, and we will overcome this using the in week 10. Okay, using some different technique in sample method techniques.
Okay.
Okay, so this is one misclassification impurities measure, which is called misclassification error. There are different as well, which are used for making the decisions. Okay, so misclassification error generally is not used for splitting our data set. It's just used for finding the evaluations or for evaluating our model. Okay, so the next, which is commonly used, is Gini index. It is defined as it is sum over pik into 1 minus pik, right? So if you notice this terminology, pik 1 minus pik is if we have feature which has only two classes. So p into 1 minus p will be what? It's a variance, right? It's a Bernoulli data set because we have only two classes. So p 1 minus p will be the variance. So actually Gini index captures the variance into the data set. Okay, so this is one misclassification or not misclassification, the impurity measures that is commonly used for finding the split. Okay, so lower value of Gini index means what? There's less variance in the data set, and a higher value of Gini index means what? We have the higher variance in the data set. Okay, higher randomness in the data set. Okay, so which one is better? You want Gini index to be lower or higher?
Lower.
Lower, right? And the maximum value of Gini index is 0.5. And the value of Gini index lies between 0 to 0.5. So if it is 0, in the case of pure node, it will be 0, right? So let's take one example to understand this, how we calculate the Gini index. So let's take one example, this particular example. Give me 1 minute.
This is basically used to find which feature to do the split on from the root node, right?
Yeah, exactly. We are defining these measures to quantify which how to decide over to split, which feature to use over the split for the splitting, right? Okay, so you will take this example to find the Gini index. Okay, so in this example we have 4 features: outlook, temperature, humidity, wind, and the level is play, no or yes. So we need to find the Gini index for outlook. Okay, so how we if we let's assume we are dividing our data set using the feature outlook. Okay, so this is your root node. In the root node, you're dividing our outlook. So if outlook is so outlooks take value 3, right? Sunny, overcast, and rain. So if it is rain, all the data points come here in this node. If it is sunny, it comes into this node. And if it is rain, overcast, all the data points come here. So look, D1, D2, D8, D9, D11, all these data points come here. Okay, so if you look here, so D1, D2 belongs to class no, and again no, and so how many data points here? 1, 2, 3, 4, 5 data points belongs to here, out of which 1, 2, 3 are 3 no's and 2 yes, right? Similarly, if it is okay, so this is sunny, not rain. Similarly, if
initially we said it is only binary tree, right?
Yeah, but in the case of numerical features, it is only binary. But in the case of categorical features, we take the classes to split our data set.
Okay.
Okay. So if it is rain, so how many data points belongs to here? D4, D5, D6, 1, 2, 3, 4, 5. 5 data points belongs to here, out of which 1, 2.
2 are no.
1, 2, 3 are no, right?
In rain.
In rain, okay. 1 and 2
are no.
2 are no and 3 are yes. Yes. And similarly, total 14. So 4 data points belongs to here. 1, 2, 3, 4. Out of which 1, 2, 3, 4. 4 are layers, right? So this is your this is now your pure node. So we need not to split this pointer. We can make the prediction. So this is now your leaf. If we are splitting over using Outlook now. Okay, so we need to find the Gini index for this node. Okay. So how you will find? So Gini index is what? Sum over pi 1 minus pi. Okay. So for this particular node, what will be p no? P of no 3 by 5, right? What will be p of yes? 2 by 5. So what will be the Gini index here? 3 by 5 into 2 by 5 plus 2 by 5 into 3 by 5, right?
Right.
So this will be your 2 into 12 by 25, right? So this is the Gini index of this particular node. Now we have to find the Gini index of this node. So what will be this?
Same.
It'll be the same.
Yes. Anyone saying something?
It will be the same because the numbers are same.
Yeah. So this will be 12 by 25, right? What will be the Gini index of this node? What will be the Gini index for this node?
0, no?
Yeah, 0. For pure leaf Gini index is always 0 because its probability of class yes is 1 and probability of class no is 0. So it will become 0, right?
Right.
So for 2-class problems, this Gini is very similar to the variance for binomial distribution, except that n term. Yeah.
Okay. So now we have to find the Gini index for the split. So what will be the Gini index of the split? So this is the Gini index of this particular node. So we have to take the weighted sum of this Gini index. Okay. So Gini index. So what will be the weights here? Weight will be the data points. So here out of total 14 data points, 5 belongs to this node. So the weight here will be 5 by 14. And similarly, 5 belongs to here, so 5 by 14, and 4 belongs to here, so 4 by 14. Okay, so the total split, total Gini index of the split will be the weighted sum of the Gini indexes. So what will be the Gini index here? 12 by 14, 25, and what will be the weight? The proportion of the class, proportion of the data points. So 5 by 14. Plus similarly, 5 by 14. 12 by 25, and here it was 0, so we need not to worry about this. So this will be the total Gini index of this split. Okay.
Could you repeat the last part?
Sorry.
So could you repeat the
So here we have found the Gini index of these 3 nodes. Okay. That you got how to find the Gini index.
But the 2 nodes Gini index is the same. So now what conclusion do we come from that?
Yeah, we are coming to that. So our question was which feature to use at the decision at the root node, right? This was your question. So what we are finding, we will find the Gini index for all such features. We will find the Gini index for overflow. We will find the Gini index for temperature, for humidity, wind, and we will see for which feature it is the lowest. Okay. So we have checked for Outlook. If we use the feature Outlook at the root node, our Gini index will be this.
So can you explain the split?
So here we have found the Gini index for these 3 child nodes, right? You have got the how to find the Gini index for these child nodes using that formula 1 or similar 1 minus p, not 1 minus pi, 1 minus pi, and sum over all such pi's, right? For all our i's. So using this formula, you can find the Gini index for these 3 nodes, right? Up to here, you got the point how to find the Gini index for this node, and this node.
Yes, sir.
Okay. Now I'm to find the Gini index of this split. I mean, what I mean by this, if I choose Outlook to split a data set, I will split into 3 nodes, and total Gini index of the split will be what? It will be the sum of our Gini index, weighted sum over the Gini indexes. Okay. So what will be the weights here? Weight will be the proportion of the data points. So here we have 5 data points out of 14. Total 14 points were there, right, in the node, root node. But in the child node, here 5 data points were there. Here it was 5. Here it was 4. So what will be the weights here? 5 by 14 for this node, 5 by 14 for this node, and 4 by 14 for this node. Okay, so total Gini index for the split will be weighted sum. So weighted sum of the index, Gini indexes. So 12 by 25 was the Gini index for this node. And what will be the weighted sum? 5 by 14 into 12 by 25 plus 5 by 14 into 12 by 25. Okay.
So where did you get 12 by 25?
12 by 25.
Yes, sir.
This is the Gini index for this particular node.
Okay.
Okay, this is 3 by 5, 2 by 5 plus 2 by 5 into 3 by 5, right?
So we have, this is only for rain, right?
This is only for Outlook. Outlook.
Sir?
Yes.
So now we have now that we have calculated the Gini index, so if we break this if we separate all this in the on the basis of Outlook, we will get this Gini index. So does that mean that how much variance it is able to explain?
Yeah. So after the split, this much of Gini index we got. This much of variance, total variance we got after the split. Okay. So we will look for which feature the Gini index is the minimum. Okay. So we have checked for Outlook. We have checked for Outlook. If we divide our data set according to Outlook, we will get this much of Gini index, right? So let's call this K1. This is some constant value. Let's call it K1. Now we are not gonna find this value. Now we will check for different feature. Okay.
Yes, sir.
So
But
let me erase all these things.
Sir, but my question is, so we are looking for the variance each feature explains while it is in the root node.
Sorry, I didn't get your point.
Actually, sir, I am understanding like why this Gini index is giving us while beginning the at the beginning of the explanation, it told that the Gini index explain us the variance.
Variance in the data set, yeah.
Variance in the data set. So here we are seeing like if the Gini index, let's say of this Outlook is 0.6. So what does that mean? Like
no, I'm not just okay. So 0.6 cannot be the value of Gini index. It's the Gini index value always lies between 0 to 0.5. So highest value of Gini index is 0.5. Okay. So if it is close to 0, it means that there is less randomness into the data set. Remember, if the node is pure, then Gini index comes out to be 0.
Yes.
Right. It means all the data points belong to same class.
Okay.
Okay. Let's say you have a node which have 1 point which belongs to class 1 and 99 point which belongs to class 0. Okay. So here you will have Gini index very close to 0 because there is very less randomness into the data set.
Yes.
Right.
So we won't
okay,
want
and
that.
let's say you have the data one node which have 50 points which belongs to class yes and 50 points which belongs to class 0. Now in this case, Gini index will be what? Highest, and in this case, if you calculate, the Gini index will be 0.5. You can find it out as well because the probability will be what? 1 by 2, 1 by 2. So what will be Gini index? 1 by 2 into 1 by 2 plus 1 by 2 into 1 by 2. So 0.5, right? 0. So if we have equally divided data set in a node, then the Gini index of that node will be 0.5.
Okay. Okay. Sir. We are wanting the highest Gini index.
We want lower the Gini index, lowest Gini index, because we want less randomness in the nodes, right?
Okay.
Okay. So we have checked that if we split our data set of using our cast, then we got some value of Gini index to be K1. Okay. Now we will check for temperature. So if we split our data set using temperature, then how will be the nodes? So it will take hot, mild, and cool. Okay, so how many data points will belong to this node?
Four.
If you see this data set, 1, 2, 3, 4 data set, right? Out of 4, how many years? 1 and 2, 2 years. And how many nodes? 2 nodes, right? Similarly, if in this particular node, mild, how many data set? 1, 2, 3, 4, 5, right? Again 5. 1, 2,
6.
4, 5, 6. 6 data points. And out of which, how many years? 1, 2, 3, 4. 4 years. It may be wrong, but you just calculate these values and 2 nodes, right? And so how many will be there? 4 data points, 4 pool. And out of this, 1, 2, 3 years, right? 3 years. 3 years and 1 no. Okay. So now we will find the Gini index for this particular thing. Okay. So what will be the Gini index here?
2 by 4. 2 by 4 plus
equally
2 by,
divided. Equally divided. 2 years, 2 no.
yeah. So it'll be 50%.
0.5.
Yeah.
Highest, right? Here. So here it will be 4 by 2, 4 by 6.
So
right?
here it'll be 0.25.
Where?
In the first one, because you're saying P into 1 minus P.
You're
taking
so it
variance.
will be 1 by 2 into 1 by 2 plus 1 by 2 into 1 by 2, right?
Okay, okay. Yeah, we have to take both. Right, right.
Okay, so what will be Gini index here? It is 2 by 3 to 1 by 3 plus same, so into 2. So it will be 4 by 9, right? What will be the Gini index here? 1 by 4, 3 by 4 into 2, right?
Into 2.
6 by 16. So what will be the Gini index of split?
You'll have to take the weights now.
Weights,
so you will take 4 by 14 into 0.5.
0.5
then 6
plus
6 plus 6 by 14 into 4 by 9. Yeah.
4 by 9 plus
Plus 4 by 14.
6 by 16. So you will get some value for Gini index, right? Say so. Similarly, you will find the values, all Gini index values for all 4 features: outlook, temperature, and relative wind. Let's say so. Gini index comes here: K1, K2, K3, K4, and you will check which one is the lowest. So if it is K1 is the lowest, you will split your data set using outlook. Okay. Now we have divided our data set into using outlook. We have done one task. We have chosen which feature to use at the root node. Okay, once it is decided, we have to use this procedure till we get the fully grown tree. What is fully grown tree? Fully grown tree means we keep on splitting until we got all the pure nodes. Okay, or we come to at the stage where we cannot further split our data points.
So the next will be the other features. The next branches.
Similarly, let's
Outlook.
say now here we have 5 data points, 5 data points, and 4 data points, right? Something like that we have the structure, right? So similarly, we have to split this node, and this node. So here, if I remember correctly, it was coming out to be pure node, right? So we will not split this node now. We will split this node. So here we have 5 data points. Okay, so we will again divide using one of these features. Okay, one of these 4 features. So same procedure, we will find this. We will check which feature to use for splitting using Gini index.
Clear.
Okay. Okay.
We should calculate it again fresh, or we use the previous value which we calculated.
We have to calculate it again, right?
Based on this particular nodes.
Yeah, based on this particular now data set has reduced to 5 data points. Here it was 14 data points. Here we have reduced to the 5 data points. Okay, so the same procedure we will follow, and we will split these data points. Okay, and your last data tree may look something like that. So here we have used entropy rather than Gini index. So any of these measure you can use. There's not much difference into entropy and Gini index.
Sir, one thing, sir.
Okay.
So we are going with the lowest Gini index. So let's say my Gini index is 0. So in that case, I will have only one class in that feature.
One class. Lowest means it can be so it's not, if it is 0, then you have only one pure node. Yeah.
one pure node. That is what I'm saying, like one pure node. So how are we going to like split based on that? Like any node we split. What I'm trying to say is every node will give me yes only.
No, I didn't get your point. So this is how your structure will look like. You have divided your data set using Outlook, right? So in if it is sunny, then data set will reduce to these 5 data points.
Yes.
Something like that, right? So if it is overcast, then you have all the pure nodes. So this node you need not to split further, because now you can make predictions for this node. Okay, and these 2 nodes, sunny and rain, we can split it further. Okay, so this is how your entire tree will look like.
So we don't have to use all the features, like only the relevant ones, right?
Could you please repeat?
So we don't have to use all the features, like we only have to take those features which are relevant here.
So for calculating, for finding, we have to make sure you can find the Gini index for all the features. So again, you have to check for Outlook, for Outlook, for temperature, for humidity, and what was the another? Wind, right? So you have to find the Gini index for this particular data set, for Outlook, for temperature, for humidity, for wind. So it's not if you have used Outlook, you cannot use again. You can use that features again.
But like all features won't be used overall.
Yeah, it may be case that all the features are not used. It may be the case that one feature are used multiple times. Okay, so here we have divided using Outlook. So for this particular node, this particular the leftmost is divided using humidity, right? And this node we are not splitting. Middle one we are not splitting because it was the pure node. And the rightmost node we are dividing using the feature wind, right? So it may be the case that we can again use the same feature, or it may be the case that one of the feature is not used in the entire tree. So here in this entire tree, we did not use the feature temperature, right?
Yes, sir.
Right. So any case may arise. So you got the point how to split, how to find the best feature, right? So rather than Gini index, you can use one more impurity measure, which is called entropy. So what is entropy?
Degree of disorderliness.
Yeah. So mostly Gini index and entropy are used, and there's not much difference between these two. So entropy is defined as minus over sum over pik log 2 pik, where we have taken sum over pi 1 minus pi. Rather than that, we can use this measure as well. So lower the entropy means that there's less randomness, and higher the entropy means there higher randomness, and the value of entropy can be in between 0 to 1. So 0 means that pure nodes, and 1 means that equally distributed data points.
Why are you taking log 2, sir?
So this is how you define your entropy. You must have come across this formula into logistic regression, right? Entropy, cross entropy.
Right.
Right. So this is how you define your randomness in the data set.
Right. But in that, we are taking natural log. In here, we are taking log.
Log 2. Okay. You are asking why base 2, is it?
Right.
Okay, so that I'm not sure about, but I think if you take another base as well, that won't affect the final outcome. But there may be case that your entropy value may go up, higher than 1. Okay, so actual answer I'm not sure about. I need to find it out.
Right.
So basically, we use log base 2 only. for finding the entropy. Okay, so these are two measures to find out which features to use for splitting, either Gini index or entropy. So we'll check for which feature the Gini index is lowest or the entropy is lowest. We will use that features to split our data set. Okay, and one more measure is as well the information gain. It is the difference between the or the say entropy or Gini index. Any of these measures you can use for finding information gain. So it is the difference between the entropy before the splitting and after the splitting, right? So we were talking about this example, this particular example where we are finding the Gini index. So let's say before splitting, what was the Gini index? So in this particular node, how many data points were there? 14. Out of which, how many years were there? 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 years, right? So what would be the Gini index of this node? 9 by 14 into 5 by 14 into 2. Right? So this is the Gini index before the splitting. Now we need not to take the weighted sum because here are only one node. There are no child nodes we are talking about. So this is the Gini index of this node before the splitting. And what was the Gini index? That was we were talking about K1. Okay, so what will be the information gain? The Gini index before splitting. So this will be what? 90 by 14 square, right? Minus K1. So this is the information gain for this. So you want information gain to be higher or lower?
Lower, sir.
It is the difference of the information gain. You want information gain to decrease down, right? You want Gini index to decrease down. So you want this difference to be higher, right? So you will split according to that feature for which information gain is highest. Okay.
So information gain is basically reduction in entropy.
Reduction in entropy, yeah. Reduction in measure. Generally, if it is nothing mentioned, use entropy as a measure. If it is mentioned, you can use entropy or Gini index, any of these measures. Okay, but if anything is not mentioned, then use entropy. Okay, so it is actually reduction in entropy.
So in this entropy also we'll take the weights to calculate.
We take the weights. The weights. Okay, so notice that we are only talking about categorical variable here, right? We haven't talked about numerical variable here yet, and we haven't talked about the regression problem as well, right? So this problem is clear. So this is called ID3. This particular technique is called ID3. So if you have any doubts till here, you can ask, or we can go further.
So I didn't understand information gain.
Information gain is the change in entropy or change in Gini index. So if it is nothing mentioned, you can say change of entropy. So for this particular example, I've taken information gain Gini index as the measure. So before splitting and after splitting, I will find the Gini index. So before splitting, what is my Gini index? So how you will find Gini index? In this particular node, you will see how many years and how many nodes, right? So in this particular node, 9 years were there and 5 nodes were there. So what will be the Gini index for this outlook? Pi1 minus Pi, that is 14, 9 by 14 and 5 by 14, right? Plus 5 by 14 to 9 by 14. So this will be your 90 by 14 square, right? So this is the Gini index before splitting. So after splitting, we have calculated as K1, right? So what is the Gini index? What is the information gain? So it is a difference between the Gini index before splitting and after splitting. So it is reduction in Gini index. So this will be your 19 by 14 square minus this one K1.
So for the next, just a clarification, but just for the next branch, K1 will become the base, right? And you find
no. So K1 was the weighted sum, right? K1 was the weighted sum. So for finding this this information gain for this particular split,
right?
So you will take Gini index here. Gini index, not the weighted sum. So here in this case, Gini index was something like, I think it was 3 by 3 by
3 by 5 and 2 by 5
into 2,
into
right?
2. You're right.
So it was 12 by 25. So you will use Gini index of the data set and after the split.
Okay.
Okay.
So it's different for all three of them.
Yeah. So for now you have find the information gain for this particular split. This is split. Now you have to check for this split. Then you will check Gini index minus after the split. Okay. Similarly for this split, let's say if we are splitting this in this node, then you will find the Gini index of this node and then weighted sum of these their child nodes. Clear?
Yes, sir.
So based on Gini index, we are splitting this. We are deciding whether which one to
Features,
take.
which features? Yeah, based on the Gini
So
index.
like information gain also used for same.
Actually, information gain is just the reduction, right?
But we
Yeah,
can
like
use
why do
information.
we? Yeah, why do
Yeah,
we
you
use?
can use any of Gini index and
Yeah.
information gain or entropy. Any of these three you can use.
All these are like same usage.
Yeah, mostly
Anyone?
they will work same, but in some of the cases Gini index and entropy may give you different trees, but in most of the case you will find they will give the same tree.
Okay.
Okay, but there may be some cases where they may give different tree. So this is all about categorical variable. What if there is any numerical features? Let's say in this particular data set, this data set temperature is given in the values. So let's say your values are given here, 20 degree, 21 degree, not so this will not be hot. So this will be, let's say 45, 47, 43, mild is, let's say 30, 31, cool is, let's say 17, 17, 18, 15, 29, what's it, 10, 9, 20, 29, 32, 31, and let's say 41 and 40. So some values. So now temperature is your numerical features, right? So how you will find the Gini index in the case of if you are splitting according to temperature? Any idea? So remember, first we have to find which threshold to use, right? If we are splitting according to temperature, which threshold to use, right? How you will find threshold first? How you will find the threshold?
So we can see the minimum and the maximum, and we can find the middle point in that.
Okay, so we will go for all possible values for temperature. Okay, so you will go for 40. So here is 41, 40, 47. So you will check whether it is less than 41 or greater than 45. This is 45. So it is greater than less than 41, 45 or greater than 45. Then you will go for 47, then go for 43, go for 31, 17, 18, 15. So all possible threshold you will check. And then you will find the Gini index, and then will for which threshold it is the minimum, you will choose that value as the threshold. Got the point? So for this particular example, let's say I'm to find Gini index if I'm splitting our data set using temperature. Okay, so first I need to find the threshold. So what I will do, I will go for all possible values. So all possible values means what? First I will check whether temperature is less than 45 or greater than 45. So in this case, how many data points will be there? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. All points will be here. On one point will be here, right? 47. And all 13 point will be here, and 1 point will be here, right? So this is if we are taking threshold as 45. So here we will find the Gini index. Similarly, we will check the threshold to be 47. So here it is less than 47, greater than 47. So here actually there is no split, right? So this is not your threshold. So we will go for next value 43. So you will check this threshold for less than equal to 43, greater than equal to 43. So some points will be here. Let's say 12 points here. And 2 points here. So you will find the Gini index here. Let's say it is K1, here it is K2. Okay, similarly, you will check the threshold for 31. Similarly, 17, let's say the all possible values, you have find the you have find the Gini index, or it is coming out to be K1, K2 up to KL. For L threshold, you have find Gini indexes, and you will check for which threshold it was the minimum.
So basically, you've binned it into two values and made it discrete.
Yeah, made it discrete. We are making it discrete using one threshold. Okay.
Right.
So if we take this example, there are 4 attributes, let's say. Each attribute having, let's say, it's kind of quasi-continuous. Let's say there are 10 unique values, or cardinalities are 10 for each attribute. Then if you take combinations of 4, we are talking about 10 times 10 times. So it's 10 to the power 4 combinations. So it's a lot of computations.
Lots of computations.
Right. That's a big disadvantage.
Yeah.
Because in a real life situation, maybe you have 100,000 records and there are like 100 variables.
Yeah. So decision tree is,
you'll get in trouble.
Yeah, it takes lots of time. Lots of computations are there.
And also, sir, like here we decided to divide it into, let's say, 3 parts, in the temperature into 3 parts.
No. For numerical features, we only do binary split, either less than or greater than.
Okay, and if we find a suitable threshold for the first one, then again we will split, or we will stop there.
Suitable threshold means what?
Let's say I am finding a suitable threshold, or like let's say I'm if I take 24 as I will get a very low Gini index.
Okay.
So now I am getting a threshold of 24. Now I am getting 2 nodes. One is less than 20, less than equal to, and another is greater than 24.
Yes.
Now, will I have? I mean, do I have to split those nodes again, or I will stop there?
Yeah. So it keep on splitting until your splitting criteria reach, right? So again, for splitting those 2 nodes, you will use the same procedure. You have to choose which feature to use, which threshold to use. If it is feature in numerical, right?
Yes. So I will split it again. I will split it again and again. So when we will stop, sir?
Stop means there are some criteria. One is that you cannot further split it. Like in the case of pure node, right? If you got the pure node, then no need to split it further, because again you will got pure node, right? Because same data points are here, you can make prediction in that node only.
Okay.
Right? Okay. And there may be some cases where you cannot. There are not any feature according to you can split. Let's say for particular that example, let me give you one very toy example. Let's say you have data points 1, 0, 0, 1, x1 feature, and x2 feature is let's say another value is 2, 3. So it's, let's say 2, 3, 2, 3. Okay, and the feature is by label is yes, no. Let's say it is yes, and so let's say yes, no, yes, no. Okay. Now, if I split, let's say I'm splitting according to x1. Okay. So what will be the features? If it is yes, then how many points will be there? Sorry, x1 is 1 or no, 1 or 2. If it is 1 or 0. So if it is 1, then this and this point goes to here, right? Yes and no.
Yes.
Right. And if this point goes to here, so here it is
yes and no.
Yes and no. Right. So this and this goes here, right? So 2, 3. Okay. So let's say it's like 2, 2, 3, 3. This situation comes there, right? Now, if you split this point, how you will split?
On x2.
According to x1, you cannot split, because for x1 value is 1, right?
Yes.
Now, if you split according to x2, So if it is x2 is 2, 3, so you will get only this point, this data point, right? No further splitting is possible.
Yes, yes. I mean,
Right?
no features left.
No, so you are not have any features according to you can still it is not pure node, it's impure nodes, but you cannot further split this one, right?
Yeah, yeah, yes.
So in this case, you have to stop your split. Okay, or you can also set your threshold like I need at least this much of point this much of data points in my leaves nodes. Okay, this threshold you can also set. Okay, to avoid
The last person.
as the data as decision trees are tend to overfit, right? Because it keep on splitting until stopping criteria reaches, right? It further cannot be splitted. So for it means that decision tree are tending to overfitting. So avoid overfitting, we can set the criteria that I need at least this much of data points in my leaves nodes, right? So this threshold you can set manually. Let's say for this particular example, I will split it and I will not split if I get this much of data points. Let's say I'm setting 5 data points. I will split this 3 only when I get at least 5 data points in my leaves node. So remember, if I using this criteria, then you cannot split this 3 because in this case you get 5 and 4 nodes, and you are avoiding actually avoiding this this criteria because I need at least 5 data points in my leaves node. So this threshold you can also set manually.
Okay, so we will be calculating the leaf node beforehand, like how many data points we will get in those leaf node, and based on that we will stop.
Yeah.
Like if I'm getting
This is one of the stopping criteria.
okay, thank you.
That's the point. Okay, so now you can find the Gini index for categorical variable, for numerical variable as well, right? So this is all about classification problem.
So I have one doubt in this stopping criteria. Suppose one example you showed that it can't go anywhere else, it has to stop by default.
Yes. Yeah.
The second is you put in some criteria of the number of data points or number of branches you want, and you can stop there.
Yeah.
If these two scenarios are not there, then finally it will have to stop when it'll keep splitting till all the nodes are pure.
Pure, yeah, exactly.
So that means it'll do till the last point.
Yeah. So in that case, the trees will become overfit because in this case, what is the misclassification error in that case?
It'll be 0 for everything.
Training data set, right? For the training data set, you will get 0 error, but for the test data set, you may get higher error, right?
Right.
So that's how the decision tree are tending to overfit.
Right.
Okay, so now you can answer one more question as well. In the starting, we have seen that decision tree are greedy search algorithm, right? Why decision trees are called greedy search?
It kind of it goes for the information gained locally, whatever is available, and it never backtracks.
Yeah, exactly. It only cares about the international position, right? Local positions. It doesn't talk about how it behave for further splitting, right? We are let's say we are on this data at this point. It takes about this talks about only this particular node, right? It doesn't take about in total how it behaves. So in that's how this is called greedy search algorithm.
Sir, could you please repeat that part, sir? Last part.
No, I was just trying to explain that why this is called greedy search. So it takes care about the local positions. Let's say we are on the root node. Okay, so we are only looking for this particular split. We are not talking about what happens in. So let's say you got overlook at the best splitting feature, right? Okay, and you have divided your data set into this, let's say output, something like that, and same thing again you have divided something like that. Or it may be the case that your best tree is something like that. It's the temperature and this thing. Okay, but what happened here? We only take care of this particular node, right? At this time. So in that manner, it is greedy.
Okay, sir.
So you said that when we have features, but like when we are not left with features, then we cannot split further. So in that left node, you have no and yes both at the leaf node. So if a data point occurs in that region, will it predict it to be a yes label or a no label?
So majority class is predicted. If there are if there are same classes, then you can further split it. And if you're not further splitting it there, so you can randomly choose any of those.
If I have two more yeses, like there are more yeses, though I will take probability of that, and then like I will say that yes is the answer.
So you have 2 yes and
one no at the
one no. So what is the measure? 2 yes, right?
Yes.
So this is your prediction.
And if it's same, then random.
Sorry.
If they are same, like one yes and one no, then I'll just take random of them.
Random of these.
Okay.
I think maybe the one interesting point is once we complete a decision tree, essentially we end up with a bunch of terminal nodes. So the way to visualize this is you take the entire population, split into, let's say 10 or 20, let's call it 20 nodes.
Okay.
So we analyze each of the terminal nodes, look at what is the majority class, and our prediction P hat is essentially each member or element in the node, terminal node, is assigned only one class, which is the majority class.
Yeah.
And the other technique we learned in the course is logistic regression. We could have done, it's a binary target variable. We could have done logistic regression where we are predicting a P hat. There we are taking a threshold to convert into, like, majority, like, but that's a threshold driven. This is, we do a nonlinear boundary to define the majority class. So that's the, I think, big difference between these two methods. But this method is slightly more greedy, and we can find a local
it's greedy.
much better.
One more is tend to overfit.
Yeah.
Decision trees, most of the cases, decision trees are tend to overfit.
Yeah, so we do not, I don't know, I was hoping we'll talk about pruning and cross-validation. And secondly, Ross Quillan, who developed this, there's also better one like C4.5.
Okay, so we have two methods here, pre-pruning and cross-pruning, complexity pruning, that we will talk about here. And best way to avoid the overfitting or overcome the problem of overfitting is in sample methods. Okay, so that in sample method we will talk about in a week time.
Okay, sir.
Here we will talk about the complexity pruning.
Got it.
Okay. So this is all about the classification problem. What about regression problem? So you have two measures, Gini index and entropy. In the case of classification, what about the regression problem? Can you think of any measure? Very standard measure is there for the case of regression. Okay, so what will be the predictions first? Tell me what prediction you will make. Let's say in this case you have some level, numerical level. So your problem is regressions. So can you suggest me some level here, numerical level?
So let's say you put a whatever solar panel, you can have a label how much energy is the solar panel producing.
Whatever. My point is that you have regression problem. Here is a numerical level, right? Some values, 35, 36, something like that. Okay. So you have a regression problem. Now you have splitted your data set into two nodes. Let's say this node and this node, and some data points belongs to here. Let's say 9 belongs to here, 5 belongs to here. So how you will make prediction in this node?
Average of.
Yeah, exactly. So average will be the prediction, and what will be, how you will find the what will be the measure to find the best split? Very standard measure is there. We have used in linear regression as well.
SSE.
Yeah, sum of squared error, right? So you will check the actual predictions, actual levels and the predicted levels, and you will find the sum of squared error, right? So this is the measure you use for the case of regression problem. Got the point? Can you do that? Okay. So let me see if there is any. So I think in the lecture slide, regression problem is not given. Example for regression problem is not given, but it is you can find out, right? How to find the best split. You want sum of squared error to be lower, right?
So here you're saying when the labels is a regression, right?
Labels are numerical.
Continuous, yeah,
Continuous.
or numerical. But my features are discrete.
Yeah, features can be numerical discrete as well.
So then, in my features are discrete or categorical. How will I use sum of squared error?
Yeah, so that is my point. How you will find. So let me give some example quickly. Let's take an example. So all the tasks will be clear. So question is the same. Which feature to use for the splitting, right?
Yes, sir.
So let's say this same example, but a bit, and let's say this is your numerical feature. One numerical feature, three category features. So this is your numerical features. Let's say some values here. Okay, so some numerical values, and this is your label now. So what is your label? Give me any label for this particular example. Okay, let's say this is cricket data set. So this is your weather and how many over were played.
We can use centimeters of rain also. I don't know. You can use
whatever. Your question is this is a regression problem. So let's say some values, numerical values, 30, 50, 51.2, something like that, right? 70, 78, something like that. And so these are numerical features now. All these values. Random values I'm taking. Okay, so now this is your regression problem. Okay, so same problem, same questions, which features to use for splitting. Okay, so you will find sum of squared error for all these three features for outlook. So let's say for outlook. Okay, so for outlook, how you will divide your how you will split your features according to, because it is categorical, so you will find sunny, rain, overcast, right? So in this node, how many data points will be there? So in the sunny, in the sunny, 1, 2, 3, 4, 5, this 5. So these data points. So let's say data points have values 50, 90.5, 72, something like that. So what will be the prediction in this node? Mean of this. So let's say mean is 40, mean is 70, 78. Okay. So you will find sum of squared error. So what will be this? So sum of squared means actual minus predicted. So you can find this. Let's say this value is coming out to be 1, right?
Got it, sir.
So similarly, you will find sum of squared error here and here, and we will take the weighted sum. So that will be your total sum of squared error, right? Or you can say here prediction is 78. Here, let's say here prediction is 70, 84, and here prediction is 69. So what will be sum of squared error? Actual minus predicted, okay, and sum over all these things, right? So this is how you can find the sum of squared error for this particular split.
Right.
Okay. Now let's say you have to find using temperature. So here it is more involved because for each and every value of possible values of temperature, you have to make a split, right? So so you have to iterate over all such values, and iteration means here prediction will be changed every time because you will have different data here. So different SSC will come. So according to that, for which minimum is SSC, first you will choose the threshold. So let's say threshold is coming out to θ1. Okay. So first you have found the θ1 and you will make predictions, and then you will find SSC here, total SSC. So once you have found SSC for outlook, temperature, humidity, and wind, you will see for which SSC is minimum. That feature will be used for splitting.
So here it's both the feature plus the threshold combination, right? Not just the feature, because everybody essentially is competing here, right? In this example.
Yes.
Yeah. So that's why the Cartesian product of all the cardinalities are actually my choice set.
I didn't get the last point.
So for example, here in this example, we have 4 features, right?
Yes.
So let's say my first feature outlook has 3 values. Cardinality is 3, sunny, overcast, rain.
Yes.
Right, 3. So I can write like number of levels equal to 3 for outlook. Temperature is hot, mild, and cool. So it has also 3 levels.
Don't call it those levels. These are classes, or you can call these levels. We are particularly calling the output, right?
No, I'm talking about it's a categorical variable. Yeah, it's a cardinality of a categorical variable. Let's put it that way, right?
Yes.
I can call this a categorical variable, and what is the cardinality of my categorical variable, right? So first one, outlook is 3, temperature is 3, humidity looks like high normal, so it's 2. Wind is strong and weak 2. So basically, my total combinations in the data set is 3 times 3, 9, 9 times 2, 18, 18 into 2, 36, right?
Okay.
So here my combinations are 36. I mean, it's a unique case. Usually your number of observations n should be greater than that, but somehow there will be a lot of combinations which do not exist in the data, right?
So you are checking how many iterations we are finding, right?
Exactly, because from a computational efficiency, see, I know it's a toy data set, but in real life, it will
be very lengthy computation. Yeah, very lengthy.
So that is what, when we are basically, let's say we start with the root node and we are making a first question is, out of these 4, which one should be chosen as the first attribute to split our root node, right? That's the first question, right?
Yeah,
in order to determine that, now in this example, toy example that we are looking at, we have to look at all 36 combinations, right? Let's assume that my
temperature also, you are missing out temperature.
Yeah.
Temperature, all possible values you have to find threshold.
Oh, okay. So if you have a continuous, then my life is even more difficult. Essentially, your cardinality is more for a continuous variable.
Yeah.
But the concept is still the same. So essentially, you are changing all combinations, where combination is multiplication of cardinality of each attribute.
Yeah, you can see that.
Yeah.
Okay. So in the sum of the books for the numerical variable, let's say, so I was talking that you can take the values, here it is 41, 45, something. So we are taking threshold as 41 less than or equal to 41 greater than 41. So some of the books you will find that it takes the median, right? So it takes less than or equal to 43 greater than 43. So you will have the same data points, right? In this case, right? So that is also possible in some of the cases, but in our course we are taking those values as only these values as the threshold. Okay, possible thresholds.
So if it is median, it'll be only 2 branches.
No median, then you have to look for all other medians. Here medians for 41, 45. Let's say here is 29. So you have to find median of this.
Okay.
So same thing, but in different manner.
Got it. Okay.
So this is the candidates of threshold. So which candidate to choose for threshold?
So in this case, each attribute has basically 2 cardinalities, to less than median and greater than median. So it's 2 to the power 4. So 16 instead of the 36 that we discussed. Yeah. So it makes things simpler.
So in the median method you are discussing, median and mean will be the same, because you are taking 2 at a time.
Only 2 at a time.
2 at a time. Yeah.
So it actually mean not median. Median, what is median? Median is actually the value, right? Observation itself, 41, 45. So median will be actually the observation itself. So it is sorted in the sorted values. So what is the middle most, right? So in the case of 2, it is the mean itself.
Mean itself, yeah, not even, yeah. Median will be the observation.
So
right?
calling it a mean is good rather than median.
Right.
Okay, so this is how you solve the regression problem. So you have seen classification problem, regression problem, both in the case of categorical feature and numerical features. So we have two algorithms called ID3 and card. So we have discussed here it is a card, and what is ID3? ID3 make assumption that the features are categorical. That's it. So we have it's just improved version of a card is the improved version of ID3. That's it.
What is CART in this?
CART actually is a classification and regression tree.
So this method of doing it is called CART. This
CART, yeah.
entropy or
This
Gini.
method is called CART. Yeah.
Okay.
So if all the features are categorical, then you can call it a ID3. So you can call ID3 is a subset of CART. Not calling subset is not good because these are algorithms, different
Right.
algorithms. So CART is the improved version of ID3. Okay. Now we have seen how to design a tree, and we have seen up to what point we can go. So, and one problem we have seen of overfitting, right? So how to overcome this problem? So there are two methods. One is called pre-pruning, and another is called post-pruning. So pre-pruning is you don't grow the full size tree. What I mean by full size tree, you cannot further split the nodes. Okay, so this is why this is what I mean by full size tree. So rather than creating full size tree, you just set a stopping criteria by yourself. Manually, you set the stopping criteria, and then don't grow full size tree. This is called pre-pruning. So in that manner, you also can overcome the problem of overfitting, but it is least used because how to set the threshold, that is one problem. So that's why pre-pruning is not used in common. What is post-pruning? Post-pruning means what? You grow a full size tree and then prune back. So how to find this? One algorithm is there, which is called cost complexity error. Okay, so let me go to that. So size of a tree is actually the longest path, the length of a longest path. Okay, so all these you can read it out. Pre-pruning is what? You can set the user specified threshold and don't grow the full size tree. And in the case of post pruning, you grow a full size, full length tree and then prune back. Okay, so how to prune back? There is criteria for that. This is called pruning criteria, and this is how you define a cost function. Cost function is summation over this sum of squared error plus alpha times. So this can be misclassification error, and in the case of regression, this will be your what? Sum of squared error, and alpha is the parameter here, which is called cost complexity parameter, and norm of t is what? It is the number of leaf nodes. Okay, so this terminology is clear. This norm of t is called complexity parameter, I guess.
It's very similar to lasso, right?
Yeah, so this alpha is called complexity parameter, and this has some particular terminologies. Alpha of t is called something. Yeah, this is called complexity. Mod of t is called complexity, and complexity parameter is called alpha. Okay, so this is how you find. This is how you define a cost function. So this is your number of leaf nodes in the tree. Okay, so this alpha is a hyperparameter, and its value are chosen using cross validation. Okay, So now tell me, your task is to minimize this CT, this cost function. So let's say you choose alpha equal to 0. So how can you get minimum error in this case?
It'll be sum of square errors.
Yeah. So in this case, you will minimum error will be when you can grow your full size tree.
Right.
Right. Now alpha is very large, very large. Let's say infinity. Then in that case, when will be CT will be minimum?
I mean the root node.
When the leaves are very less.
Yeah.
Right. So in this case, the data itself, the root node itself is the best tree, optimal tree. So value of alpha is chosen by the cross validation. Okay. So what actually happens there in the cost complexity pruning? You grow a full size tree. Let's say your tree is something like that. This is, let's say, this is your full grown tree.
Okay? We can't see what you're writing.
Oh, is it? So let's say this is your full grown tree. Okay. Now it finds CT for all such subtrees. So what will be subtree? Remove this thing. So this will be your subtree. Because you will find CT for this. Now in this case, you again remove this thing. You find CT for this thing. So let's call C1. This is called C2. Similarly, you remove this node and then find CT for this thing, C3T. Or you can remove this one and this will be your for a given alpha. Okay, for a given alpha I have fixed. Okay, for this will be this node, this subtree. So this calls C3T. Similarly, for all some possible subtree, you will find a cost function, value of cost function, and then choose for which it is the minimum. And you for that particular alpha, you choose that subtree to be the best optimal tree. Okay. Now you will find such optimal trees for different values of alphas. Okay. So these alphas are chosen using cross validation. So this is a hyperparameter. So out of these optimal trees which is found for given alphas, alpha 1, alpha 2, alpha 3, we'll find the best tree using which gives the least CT cost function. Okay, and CT is what?
Not clear, sir. That means this can be out of hierarchy of the tree when you select the best cost function. So suppose the last branch is selected as the least cost function, so that will become the top branch.
Last branch is chosen as what?
Having the least cost, the optimal cost.
Okay.
Or the minimum cost. So that branch and the leaves of that will become the top branch.
No. I'm not saying that this subtree. I'm saying that after pruning this one.
Okay.
After pruning this one, I've left this subtree.
Oh, the whole thing.
The whole thing.
Okay,
yeah.
okay. Then it's clear. Okay.
Okay. So actually, this is your subtree. Something like that. So what are my subtrees? I will prune back. It's not like I will prune this and I will get this tree. It's not like that. I will prune this and I will get this tree. So I will find the CT for this tree. Similarly, I will again prune this thing and CT. In that manner, I will prune this.
Right.
So there are a lot of combinations here. So once the tree is grown, there are we have terminal nodes. The way to think about it is every time I get rid of a terminal node, let's say in the left hand side.
Yeah.
Let's call it node 1 and node 2. I can't just get rid of node 1. I had to get rid of its
both the nodes. Both the nodes and
also.
All the, yeah. So siblings also. So all the data points will be here. Correct. Now this is your leaf node rather than this.
Correct. So that creates a, let's say this is my tree number 1. So by pruning node 1 and node 2, I create a subtree 1. Similarly, if I go to the right hand side, I've got again a lot of choices, right? So if I have a tree with, let's say, 6 terminal nodes, technically speaking, you are putting them into a bunch of siblings. And if I get rid of a bunch of siblings together, essentially I'm collapsing these 2 terminal node to the parent node. That's all I'm doing, right? I'm basically pruning.
Yes.
So it creates a new configuration. See, in other words, the hypothesis I'm testing is it, am I overfitting? Am I overfitting, meaning maybe the parent tree, a parent node should have been the leaf node, but we got greedy and we split the parent node further into child, right? So the idea here is, let's say we are greedy, that's our hypothesis. If we prune the leaf nodes and merge it to the parent node, essentially this is where we should have ideally stopped. Yeah, that is exactly what we are kind of testing in our cross validation. I mean, in this cost function calculation.
Yeah, exactly.
Right? But problem here is again a lot of. I mean, imagine tree itself is a very very computationally intensive
complexity
process.
Is a problem. Yeah, complexity is always a problem with the tree.
So if a tree has 20 leaf nodes, let's say assume it's a binary tree, so that means 10 pairs of siblings. We're already talking about 10 subtrees. If I only stay in the level 5. Let's say it's a 5-level tree, level 1, level 2, level. I mean, so they are also going to see, am I going to only prune the last layer, or am I going to allow to prune even go to level 3? For example, I had to roll up the tree up to level 3. So these are all questions that we have to answer.
Yeah, right? Complexity is all very disadvantage of a decision tree. So this is a main 3 disadvantage of a decision tree is always tends to overfit. Most of the cases is tend to overfit. Second is complexity, because you see the computations. Is every node it takes over every features and every possible values, right? So that's how it's very complex. But advantage is what? It's very easy to understand. Second, it solve both classification and regression problem. And one thing, it needs very little data pre-processing, because we don't make any assumption about the data set, and we need not to standardize or normalize our features at all. So it requires very less data pre-processing. And one more advantage that in the initial someone has mentioned that even if we have data set which are not separated using hyperplanes, right? Something like that. Here x, 0, 0, 0, 0, here 0, 0, 0, etc. So here using a regression problem, the model will be very less accurate, right? So, but decision trees learns this kind of data set very well, rather than regression problem and any other problems. Right, because if you learn the linear regression here, so some hyperplane you can something like that or something like that. So that polynomial transformation you can do, and you can transform your feature into some different space. But think of some complex data set where decision tree can learn better than the linear regression models.
So the complexity is in calculation, but if you're presenting it to someone and if they are pruned branches, then it's a very nice model to present.
Yeah, to interpret it is very nice.
Interpretability is very good.
Very good.
You can explain in English, right? If this is less than this or greater than this. So for business users, can explain it to a marketing person.
Yeah, interpretability is very good.
Very good. And people love it actually, because it's very powerful, nonlinear decision boundary. Yeah. You can explain
even
it
though
easily.
Anyone who doesn't understand and doesn't know anything about the machine learning, you give him this tree, he will able to understand what's actually happening. If it is less than this, it goes to right. If it is greater than this, goes to left, right? Very easy to understand. So if you have a tree with you, you can understand easily. You can make prediction easily. Okay, so go through these slides. It will be very easy. Do 1 or 3 very toy examples. So actually find out how to find Gini index, how to find entropy, and you can solve those practice assignments and graded assignments. So such some easy calculation are given in the practice and graded assignment that you can solve.
So code implementation of week 8 is left to do.
Week 8 or week 9?
Week 8.
Week 8. So solve with the instructor is not done?
No, sir. Because of.
Okay, so I will talk to Kartik about this, and maybe he has planned something this week, for this week.
Yeah, Wednesday or Thursday would be good.
Yeah. Okay, so if it is week 8, Week 8 is not done. So first we will do for week 8 and week 9 will be on Saturday. So there we will see the Cola file and we'll do the code with Scratch in solve with instructor session. Okay, so this is all about the theory of week 9. You can read it out. Maybe I missed some points, but this is the basic idea behind week 9 decision trees.
So are we talking about boosting and all that, or that's deep learning next semester?
Sorry?
Boosting.
Boosting we are gonna do in the week 10.
Week 10? Okay. All right, thanks.
Sir, I have one question in this week 9 theory. So suppose that there is a two mathematical equation is that one is the Gini index, one is that yes. So the what is the actually the how this actually this particular logarithmic equation came to exist to decide this equation? So
how this exists?
Yeah. How someone proposed that this is the equation which will
for finding the randomness in the data set, huh?
Correct. Because that and they decided that okay, based on that probability, they decided. So, what is the background of this mathematics? So,
so Gini index, for Gini index, I have some idea, but not about the entropy. I've read it out, but it's slipping my mind. Okay, so for entropy, I've read it out how the formula comes in, but for now I cannot tell because it's slipping my mind. For Gini index, right? Gini index is defined as sum over PIs 1 minus PIs, right? So if you notice this, so this is what sum over PIs minus sum over PIs star, right? So what is sum over PIs?
1,
right? So 1 over sum over PIs square. So let's say you have 3 classes, so you can find in this manner 1 minus P1 square minus P2 square, something like that. So this is actually what is this probabilities, right? Probabilities of that class, that example of belongs to class 1 for that particular node. Okay, so we are finding 1 minus something. So it is actually capturing the randomness, right? This is the probability of that class 1. So if you look at this expression clearly, we are finding 1 minus probability of that class, probability of class 2. So close to 0 means, okay, give me 1 minute. Okay, so sorry for the interpretation. So that's how you find the Gini index, right? So this captures the randomness in the data set.
Okay. So my question was even that back of that, like that summation of PI and the 1 minus P, that how that from logic actually that most of machine learning thing we are applying in mathematics from the logic for the real world scenario. So how actually this idea came to make this, okay, this particular formula is going to decide there. Is that any reference you can suggest me where I can go? If I use that particular process, it's okay. We can program, we can write that. But the question is that whenever we need to some situation comes like that where we need a modification, we need to add our point.
Okay.
For example, sometime I was thinking something to solve where the linear regression type of thing was there, where the weight was there. No, whenever we do, there is a in linear regression, there is a weight.
Sorry,
there
is a what?
In the suppose that there is a linear regression problem
Hmm.
where we write the XW matrix, where
Yes.
the every feature is multiplied with the some weight.
Hmm.
Okay. So there was a situation because it will not solve all problem. What will happen? Sometimes weight itself is the not a constant, because in whatever weight we find, it's the constant. But sometimes weight can be varied with time also. Is it, sir? I thought about that. For
No,
example,
for different value of weights, you will get different models, right? For
no,
different values of weights, you will get different model. Out of those models, you try to find out the best one.
so it is also certainly possible that with time, same model, in the same model, W also can vary. What
Okay,
happens?
so in that case, you don't have a single model. You have different model. So if you are varying your Ws, then you don't have a single model, because for changing W, your model will change.
Okay, so we can't make that W variable dynamically.
So maybe the question is this, right? So let's say you are a data scientist, you're building a model today, which is 27th June 2022. So you generate 1,000 models, and for each of those models, you find a W, and you pick the model which has the lowest SSE, and it has a corresponding W, and that becomes your model. You fix it. Now you implement the model, right? Now life goes on, the business or user keeps using it. Now over time, you start producing the AUC curve and whatever, all the diagnostic we learned, right? And you will see the model's performance is deteriorating over time. So there will be a certain point in time you start to question, okay, why am I sticking with this model that I developed? Maybe the data has changed, time has changed, customer preferences have changed. The model that I used to model consumer behavior, whatever you try to optimize, has changed. So in that case, you will actually develop the model again. So maybe in sometime in July, and then pick the W which is best for the most recent data set that is available, right? So that's a real life example of how changes in data could influence you to change the model, because essentially you are not optimizing for lowest sum of square, right? So theoretically speaking, the model can be changed every day, right? So, but of course, from practicality consideration, you fix the W and stay with it for some time.
And this procedure is called learning, right? Learning from the data.
Yeah.
You have new data, then model again will learn. Again, you add something more, that model will learn itself, right? So that's how it is called learning from the data.
Okay, so in the practical world, every time interval we update our model itself.
Yeah.
Manually.
But again, if your model competition to develop the model, you have to train some resources and it's taking 6 hours to train a model, you can't do it daily, right? Because you are going to disrupt your current process, right? So that's why it's a trade-off, right? Maybe you train your model over the weekend when there is no transaction. Let's say you work for a bank, right? You can't change your model to decide your algorithm to approve or decline a customer, right? You can't change in the middle of the day. There is also rules. You can change the rule of the game in the middle of the day, right? So there are a lot of restrictions also, right? So every business has to decide it's a trade-off. You want to make the most accurate decision given the data, but there are also practical limitations as to you, because of the time and resource that is necessary. When you update the model, what is the incremental gain you get really, right? Maybe is it worth enough to spend so much of time and energy, right? So that's a trade-off we do in a real life situation where based on how much the data is changing, you decide an appropriate interval to retrain your model and update your W or maybe a new model.
So in that particular case, I have one question. In all cases, our W is always constant. Is there any further theory where that the weight itself has the function of the time, or is there this type of no theory at all?
No, I don't think there is any.
Okay.
Because if W becomes function of something else, then you don't have a fixed model.
Yes, no, it is fixed model for the particular instance of the time.
No,
Because
I don't see any model
like that. Yes.
Yeah, like that.
Okay. Okay, sir. Okay, that was one of my question. I was thinking that to design some model, and I thought I will ask in the class. Yeah, thanks, sir.
So I think we should close the session now. For next session, we will have the solve with instructor where we'll do the coding. So you can read it out now and check the codes as well in the lectures. So that will be easy for you as well.
Thank you, sir.
Okay, so we can close the session now. Thank you, everyone.
Thank you.